Hello, this is Dr. Flight, and we're going to talk about product architecture in this particular segment. So when you think about architecture, you think about buildings, building anything that involves lots of pieces, probably. And so if you think about a product is a bunch of pieces that have to be assembled together. And so what we want to think about are all the different pieces that come together to form parts of a building or parts of a product. And then those parts come together again to actually be assembled to create the product that we want to use. So product architecture deals with the design and the engineering of how pieces go together to actually build a product. So that's what this segment is about, product architecture. Product architecture is a concept that relates to the design and the creation of the product so that it fits into a manufacturing perspective and also the customer needs. But it's a thoughtful, conscientious part of designing how the product is built specifically from an engineering perspective and also from a design perspective as well. The concept of architecture is the formation, beyond a building, beyond a physical structure of a building, is the formation or construction resulting from or as if from a conscious act or a unifying or coherent form or structure. And that really B part is kind of what we're looking at here. When we think about product architecture, we want to think about how the design is most efficiently created to manufacture, but then also at the same time is efficiently created to solve the customer's wants and needs. So the product architecture concept, as it is in the design phase, is a process by which the customer's needs are developed or built into a product based on a function of its design. So good product architecture is going to lower costs for the company because manufacturing will be done in an efficient manner because of how the product is built and conceived and put together. And it'll also help bring the product to market as well. In some literature, we think of this as subcomponent functions. So how subcomponents can be created within a product, which then become assembled. And these subcomponents are sometimes called chunks or pieces that are related to each other when they're put together. The way I think of this is if you are building a model airplane and you have the fuselage and you have the engine and you have the cockpit and you have the wing assembly maybe, or the rudders or some pieces like that. You have the wheel casings and the wheel base underneath. And so what you basically have is 5 or 6 different major components that all have to fit together. And so what you do is you think about the subassembly from an architectural perspective, and then you think about how those will be placed together in the most efficient way. So that's what we think about when we think about product architecture, and sometimes we develop this a little bit further and develop what we call a product platform. So a product platform happens sometimes here. So product architecture development's related then to different sub-assemblies or modules or chunks that can be replaced easily within the product architecture. So for instance, if you consider my airplane model example, let's say that I have the fuselage and I have the wheel assembly and I have the cockpit assembly, but at some point along the line I want to upgrade the engine assembly. So the engine assembly is a separate component or a subcomponent of the airplane, but because I have the modularization process going on, because the architecture will allow me to do it, assuming that the fuselage can handle the weight and the power and so forth of a new engine, then I can replace the engine, and that engine should be able to integrate into the product that is already there. So as a result, if you think about modularizing or subcomponent components of your product, and this can be done with a process as well, like a service, this can certainly be done there as well, then many, they call them derivative products, but many new products can be created that are like incrementally changed products. So I could upgrade one piece of the product while the whole rest of the product stays the same. For the plane example, I could upgrade the cockpit and add some new features to it, but the plane will essentially be the same for the rest. But the cockpit will be updated, so I can maybe give it a new name and a new price tag, and I can go to the market with a new product because that one component was changed. But if you think about it, my cost associated with creating that new product is only minimal because I'm only changing one version or one element of the product. The Sony Walkman is an example that's been given for many times. Over 200 different versions of the Sony Walkman, which again is a product from the 1980s, so it's a very old example, could be developed because they used a platform or modularization type of a component. Other examples like Polaroid, and being able to use the film maybe in different applications or in different types of cameras. Operating systems like Apple, Microsoft, and so forth are very flexible because they can be used on a lot of different hardware pieces. Plus, we can interchange and make changes to the different elements of the software package if needed. And then, of course, there are lots and lots of car examples, automobile examples, where you have the frame of an automobile created, and then that same frame is used for many different automobiles after that. Okay, so the platform or modularization idea really extends quite a bit from an architectural perspective. It's like building a building. You have the roof, you have the frame, you have the fit and the finish of it, you have the foundation, you have the systems like air conditioning and heating, you have plumbing. So you have all these different systems and pieces, and you take all these individual parts and you put them together and you've got a complete product. But if you want to change that product, you just need to change one of those parts, and by doing so, you have something new. So that's really what we're talking about. And as we look at the product architecture, the first step to really think about is to develop a schematic or a drawing of the different components and how the components will go together. And so when we think about the illustration here of a product's architecture, there are going to be three separate components that we're going to look at specifically here. The first one deals with what they call the product schematic, which is essentially what is being done for the customer. And we think about this as a grouping of activities. So we have the different pieces that will go into, in this example here, we're talking about some type of a musical device, or it's actually a computer with a disk drive and a power source and so forth. So the component of the recording system is a series of parts that need to be put together. And then a component of the disk drive, a series of parts, and then the output system, so how things will get displayed and so forth, and then a power source. And then what we're going to do is we're going to put these individual pieces together as a module. So the clustering of the schematic elements comes next. So we have the individual pieces, then the clustered group or the module that is pieced together. So we have one unit that comes together, and it's a component called recording. And this is an individual piece. It's a part of the overall product, which was derived from all these individual pieces. And then we have the disk drive component, and then the output component, and then the power source component. So these are the modules, or the these should be these should be where they could be modified and changed. So if I wanted to upgrade the recording chunk or module, I can change the pieces and parts that went into it in step number 1 and have a new recording device, or the disk drive. So maybe we don't have a like an internal disk drive anymore. Maybe we're going to a different type of disk drive, an external disk drive or something like that. I can change these pieces in and out. The third step and the fourth step is to number 1, create a visual layout of how these pieces will go together. So this could be how it goes together as a product, and it can also be a visual geometric layout of a factory or of a manufacturing or assembly line, if you will, as well. So of the product itself, but then also of the manufacturing of it too. And then also we need to check for the relationship that these pieces will have with each other. So will these pieces work with each other? Will they accept each other? Are they compatible? Are the modules compatible with each other? That's step 4, where we talk about checking for interactions. Checking for interactions, and will they work? And then again, if I want a new product, then I might just replace one piece. I might, take the disk drive out, and I might put a new disk drive in, and now I've got a new product. So incremental steps are what are going on here, and this is the idea behind the engineering and the thoughtful approach of an architectural design for products. So moving forward, a lot of this work gets done from an engineering and technical perspective using computer-aided design. So CAD work has been around for a long time. Lots of new changes have taken place in CAD. But if you think about it, if we can create a digital layout or illustration of our architecture, then this may very possibly save a lot of money and save a lot of time, and it allows us to try lots and lots of different product architecture variations before settling on the best ones that would be appropriate for us. Built into this, we're certainly thinking about what will satisfy the customer, but at the same time, in the design phase here, we're thinking about how we're going to manufacture this product in an efficient way. So using CAD level or computer-aided design features will definitely be able to minimize the cost. And the thinking here is that even if I can make minimal changes, like maybe I can shave off a little bit of a dimension on this piece and it'll fit better into this piece, or maybe I can use a different type of connector that's going to connect one component to the next. I may be able to find some cost savings, which could end up being huge savings over time. And it's a whole lot better to be able to do some trial and error work in the CAD environment than having to worry about it in other environments. Okay, so the design for manufacturability comes into play here when we're thinking about the design costs and so forth. We also have the design for assembly. So again, I mentioned that we could draw out a schematic of the product. We could also draw out a schematic for the actual assembly line. And this is where that helps come into play, where we can think about product flow quite a bit and how that will become efficient for us. So lots of new developments, of course, with product design, prototyping, and so forth. Stereolithography would be the creation or the drawing and the writing of prototypes. Rapid prototyping is something, especially with 3D printing, is something where we can design prototypes of fairly complex concepts and ideas in minutes, literally minutes or hours at times. 3D printing is becoming so accessible and so efficient and reliable that people can, that companies can invest in 3D printing. And also the other big aspect of 3D printing, not only is the quality improving a heck of a lot, but also the materials that are being used, that can be used in 3D printing, are expanding as well. So that's certainly a good thing. Incorporated with this is absolutely an engineering perspective. So mechanical computer-aided engineering, or developing this whole product architecture from an engineering perspective helps product developers and the R&D folks and the engineers who are working on the product design do simulated stress tests, which could help thermal flow, fluid flow analysis. Can in some part be tested, in a digital environment. So we certainly want to test from a engineering perspective the tolerances of our new products. Multi-body dynamics. So if we have different components working with each other, different pieces of a product that interact with each other, we want to make sure that they interact properly. And if they're moving parts, if they're flexible, if they're non-flexible, and so forth, multi-body dynamic testing is something that can work there. Casting, molding, again, so if we're injection molding or doing work like that, we're certainly going to do some type of computer work to design all of that. And again, from an engineering perspective, we have measuring and tolerances that are going to be acceptable. And then, performance optimization, so the performance of the product, but also the performance of the process of assembly will become something that'll be critical to us as well. And an example, just an example of some of the computer-aided design work for the auto industry, for instance, thinking about the fit and finish of sub-assemblies, making sure that pieces fit where they're supposed to fit. This is also an idea that if we have a standard size, then we need to make sure we maintain that standard size when we change modules. So if I have a platform and I've got a particular chunk or a module in it that I want to upgrade or change, I need to make sure that whatever I do will still fit in the space that is provided in the product. Again, we can work this all out from a computer perspective, and then we can maybe do some 3D printing, print up some prototypes, and then check to make sure things fit properly. This is an example attaching a powertrain to the upper body in a car, the putting together of these major modules and sub-assemblies have to fit. They have to. There's very little room for error on these types of things. As you can imagine, an automobile has hundreds of thousands of pieces associated with it. These pieces all need to fit properly, and so that's just an illustration there of how computer-aided design and the architecture that's behind, and the engineering that's behind the design really pays off. And moreover, product safety and the product use in the consumer's hands has to work as well. So as we wrap this up, we talked a bit about architecture and platforms and the concepts of modules, the architecture process, including a schematic cluster groups of modules, so the clustering schematic as well as the product schematic. And then we had the product layout, and then what's not here is also the interactions, the fourth step. The interactions between modules need to be tested. And then finally, we spent a little bit of time touching on how computer-aided design is helping us from a manufacturing efficiency, but also from an engineering. The engineering behind the product design can often be aided through a lot of computer simulated types of work. So that wraps up this segment.